Anybody have any questions? Any issues? Everybody all right? Okay, well, we left off on page 25 down at the bottom. We have 4 examples left in section 7.4, and they're really, you know, they correlate directly to a My Math Lab problem. So the one we're about to do is My Math Lab 18. Okay, that's the one that we're gonna work on now. So we're just gonna work through these last 4, and then we'll jump into the sum and difference formulas. Okay, so down here, again, it says establish the identity, which means make one side look like the other. Later on in other math classes, if you are gonna keep going, you have to decide which side to start on. And the rule is you always start on the most complicated side. Well, this side is more complicated than this side. So this is where we are gonna start because you have 2 squared functions. Over here, you just have 1 squared function. So this side's more complicated. Now in this class, I like to try to always make you find the more complicated side, but in here, it's always the left side. So you never have to guess. It's always the left side, okay? All right, so here we go. We wanna make this look like this. So what in the world step do we take first? Okay, well, we gotta think a little bit. Remember, when you see 2 squared functions, a sine squared and a cosine squared, what are you supposed to think about? Pythagorean, okay. So we want to think about Pythagorean. The problem is he has a coefficient of 21 and he has a coefficient of 22. In order for me to use Pythagorean, they have to have the same coefficient. I can't have one with a 21 and one with a 22. So let's turn this guy into, what if we separate him and we have like 1 times cosine squared theta plus 21 times cosine squared theta. What do we think about that? We could add these back together and go right back where we were, but all we did was separate them because that way, okay, that way I can combine these 2 and use Pythagorean. Does that make sense? Kind of what I did there? I just rearranged a little bit. I separated these so that now the sine squared and the cosine squared term have the same coefficient, okay? So I can also rearrange this so they're sitting next to each other. You certainly don't have to do that. This is just kind of an extra step, but sometimes it helps students see what's going on. All right, well, I really don't need that 1 out in front there. Okay, there we go. All right. And then, since they both have a coefficient of 21, that's kind of like their GCF, right? I can pull that out. And what I'm left with in here is this. Okay. And then we know from our Pythagorean identities, what is sine squared plus cosine squared? It's 1. So then this is going to be times 1, which we know is just 21. And then look there, that exactly matches the right side of the problem where we started. Sound good? Yeah, not too bad. It kind of reminds me of number 7. We did one kind of like this up number 7, the top of this page earlier. Okay. All right. Last page of identities then. Is everybody okay with what we did there? Then this equals this. So we know that it's correct. Just draw a little line up there. So it's the same thing. We know we're good. Okay. Get my oh so nutritious Diet Coke. Okay. All right, let's go ahead and talk a little bit about number 10. So number 10 on your next page, okay, that's going to be number 15 on your My Math Lab if you want to make a little note. Okay, So this is going to be like the number 15. Get it to focus in a little better. There we go. Okay. So establish the identity. Well, we want to make one side look like the other. Well, even if you're not sure, you know, well, in here, you're always going to make the left side look like the right side. But I think we all know one is a lot less complicated, right, than the other stuff happening. So we're going to start on that other side. Okay, here we go. We want to turn this big mess here into one. So I'm going to distribute, right? Most of the time when you see parentheses, you just distribute. I don't want to say every time, but most of the time. So sine squared theta times 1 is sine squared theta, plus sine squared theta cotangent squared theta. Okay, there we go. Now, proofs and identities, it's all about one more step. How can you take one more step? What would give you one more step so that you can then do a little bit more cancellation? So at this point, I'm kind of like, well, I do see some Pythagorean-ish stuff, but when you go back and look at your identities, sine squared and cotangent squared are not in the same identity. So that is not helpful. So one of those helpful hints from the first page is that if you seem stuck, make everyone into sine and cosine, right? Turn everyone into the big two, because chances are it'll give you one more step. Okay, so cotangent, now I know he's squared, but if I want to turn cotangent into sine and cosine, remember, he's a quotient identity. I can go back to here. Cotangent is cosine over sine. I'm going to turn them into that. Now I have cotangent squared, but I'm just going to make it cosine squared over sine squared. You can do that. Okay. So that's what I'm going to replace now. And that might give me one more step. Okay. I'm going to turn this into cosine squared theta over sine squared theta. Okay. I just made everybody into cosine and sine. That works a lot. Okay. Now I do see one more step really clearly. Everybody see a cancellation there? Look at here. This and this can cancel. Then you guys can take it from here, I'm sure, but I have sine squared theta plus cosine squared theta. What does that equal? 1. That's a Pythagorean. And it just so happens, what did we want our right side to equal? Or our left side to be the 1? There we go. We're done. We proved it. Okay, that one little step fixed it all. And that's what usually happens, is one little step will lead to the end. Okay. Oh, shoot. This thing keeps blurring on me. Poor Leighton. Okay, here we go. Scoot up now. All right, now this one, again, establish the identity. We're going to start on the left, but hopefully you see it's pretty clear that this is the more complicated side. Does that make sense? Because it's got more happening. It's got it's got a numerator and a denominator, so it's fractions. It's got 2 terms, so it's definitely more complicated than 2 cotangent theta. All right, well, what in the world am I going to do here? I've got secant and I've got tangent. First thing I'm going to do is the other side, the right side, is one chunk. Let's make our left side one chunk. What do we think about that? Let's combine those into one fraction, and then we can probably cancel some things out. So that's what I would recommend. Let's try that. All right. Well, we need our denominators to be the same. So tan theta, I'm going to seal him off because I don't like to lose people. So 1 minus secant. All right. So my LCD in this case is going to be each denominator, right? Just multiplied by each other. Okay. Now, even though I have an equal sign, I can't multiply everybody in the top by this because I'm trying to establish an identity. My only choice is to make these equivalent fractions that have this denominator. So this guy needs a 1 minus secant in the bottom. So I'm going to multiply his top and his bottom by 1 minus secant theta. I know that's super hard to see, but that's what I did. I'm just being lazy because we got a lot of other steps here. Okay. This guy here, his denominator needs tan theta. So I'm going to multiply top and bottom by tan theta. Okay. Now let's make it a little clearer and write it out. Is everybody okay with what I did though? I just multiplied the top and bottom of each fraction by what that denominator needed, right? Okay, so now I can have a big giant fraction. My denominator is going to be tan theta times 1 minus secant theta, right? That's what I turned the bottom into. Okay, here we go. This term is going to be 2 of these. That's what the numerator is. Okay, and that was a minus before I wrote all over it. Then over here became tan theta times tan theta. Okay, I'm just kind of taking my time, putting some extra steps in there. If you don't need them all, you could have FOILed and made tan squared theta right away if you wanted. Everybody okay with how we got that far? Okay. All right, here we go. All right, my denominator, I am going to leave him alone. Now, I just got done talking about the fact that up here on this one, we distributed a lot. But here's the thing. This right side doesn't even have a denominator. So we are going to need things that cancel to get rid of the denominator. I am not going to distribute this until I get to the very end and see if it needs to be distributed. Chances are one of these two items is going to cancel on its own. Now that's just from experience with identities, but I'm not going to distribute him yet until I know he needs to be distributed. Okay. All right. Now we got a FOIL situation here with these two. So here we go. We're going to have 1 times 1, 1 minus secant theta, another minus secant theta. What is negative secant theta times negative secant theta? Positive what? Secant squared theta. Yay. Okay. All right. Then I have a minus. I'm running out of room. Okay. What's tan theta times tan theta? Yeah, tan squared theta, right? Put your little square on the word. There you go. Okay. All right. So here we go. We're going to clean up a little bit. We have a 1. And then I have what's minus secant theta minus secant theta? Yeah, minus 2 secant thetas. Okay, now before you write anything else, you can write your denominator. Let's think about this a minute because I'm trying to save you some room here. Okay, now over here with these guys, I have a secant squared minus a tangent squared. That's 2 squared functions. That could be Pythagorean, right? That's Pythagorean-ish. It's not the ones we know, like cosine and sine. It's not the famous one, but he's both squared. Let's go to our Pythagorean identities here, okay? Sure enough, we have a Pythagorean identity that involves tan squared and secant squared, okay? Now, how is ours arranged? Ours is secant squared minus tangent squared, okay? So if I have secant squared and I subtract tangent squared, what does that equal to? 1. Everybody okay with that? Okay, awesome. So then this is going to be plus 1. All right, we used Pythagorean to do that. We thought it could be, we checked it out, we rearranged it to match what we had, it worked. Okay, now I have 1 plus 1, that's a 2, minus 2 secant theta. Still have this denominator hanging around. It's going to pay off in a minute. Okay. By the way, be careful here. About, I'd say, a third of students would tell me these 1s cancel. And it's just because this minus, even though it's not with a 1, your brain just gets so excited and it will just cross them out. So be careful, be really, really vigilant with these. Okay. All right. Now I need another step. Remember, it's all about just give me one more step. What do we see in the top? In algebra, you would do this in a heartbeat. Anybody? Rhymes with a GCF. I'll take it. Okay, so we pull out a 2. If we pull out a 2, ta-da, that's another step. Look what we just made. All right, moving right along. Okay, so we get to this part. I see a cancellation. Awesome. Okay, Now I'm down to 2 over tan theta. It's always good when you get close to the end, go back and look at what you're trying to get. What are we trying to make? 2 cotangent theta. I have 2 over tangent theta. Does everybody see the next step? It's a quotient or a reciprocal, right? I could rewrite this as 2 times 1 over tan. You don't have to write all these steps out if you see how you get there. But what's 1 over tan? Cotangent. Yeah. So there it is right there. And suddenly we're done. So there we go. Okay. Sound good? Now, in a higher level class, some of the other classes, at each step, you would have to give an explanation. And you'll see that in my math lab. Those of you that are doing your 7.4 my math lab, they'll want to know, well, how did you go from here to here? Well, you used the reciprocal, right? How did you go from up here to this? You used a quotient, right? So you kind of have to sometimes remember the names of these identities. Oh, and by the way, this one was number 19 and number 12 is number 20. And then that finishes off my math lab for 7.4. Is everybody okay with this middle one? Good. Okay, this guy down here is actually extremely easy. So he'll be real quick. Okay. All right, so here we go. We want to make the left side look like the right side. Hopefully you see this is more complicated than this. You guys would rather be beat than have a fraction in math, I know. So this is gonna have to turn into this. All right, we need a first step. Well, let's think about this. We want to end up with how many terms? 2, so let's separate them. Up here, we wanted to end up with how many terms? 1, so we combined them. You kind of see how that works? So it just gives you a starting point. However you want to end up, think about whether you're combining or separating. So here, I'm going to separate. Okay, so I'm going to take cosine theta over the denominator minus secant theta over the denominator. All I did was separate, okay? Once you separate, you have some cancellations right there at your fingertips. This one comes together really fast. So this first term is going to turn into 1 over secant theta. The second term is going to turn into 1 over cosine theta. All right, when you look at the right side, you want to end up with cosine minus secant. You don't want any fractions at all. So how do we go from these to these? Okay, or make it even easier, they're just reciprocals, right? They're just reciprocals. So 1 over secant theta is the same as cosine theta. What's 1 over cosine theta? Secant theta. And you're done. Yeah, if you go to LCD, yeah, you could multiply them. You'd have a whole nother paper, but you'd get there. It's all right. Okay. All right. Sound good? Okay. It's kind of like you're on the turnpike and you miss your exit, so you got to go down and work your way back up. You just missed your exit, but you'll come back. Okay. Sound all right? Okay, that's 7.4. So there you go. Again, name of the game is I need another step. So anything that's going to create one more step for you. Okay. All right, let's turn it on over. Now we have 7.5. Okay. So these are sum and difference formulas. Sometimes you'll see them called sum and difference identities. I think even my math lab goes back and forth. Sometimes you'll hear me go back and forth. So it just depends. But there are 2 formulas for sine, 2 for cosine, and 2 for tangent. Tangent's buried in here somewhere. We'll get there eventually, hopefully today, but we'll see. Okay, so what in the world are these things? Because they've got all kinds of symbols and they look hard. They're not hard. They're really a handy little tool for when you need to find an angle that is not explicitly given on the unit circle, but you are on the unit circle, but you don't see it. So this is where you need to create it. This lets you do that, okay? A lot of times I derive different formulas and identities for you guys. I'm not with these because it's a long process, but if you really want to, Google it. It's kind of interesting. This comes from the the distance formula. Remember that from geometry and algebra and all of that stuff? So all they did is they took 2 points on the unit circle, point alpha, point beta, and they put them in the distance formula, and they did all the work, and it shook out into this, believe it or not, with some identities in between. So that's where they came up with these. So anyway, you're going to have 2 points. Don't let the symbols intimidate you. This is alpha, right? I usually draw him like a little fish. This is beta. He's just a bee with a long tail. This just means 2 angles that you know. That's all. That just means angles. Alpha and beta are angles. Angles that you see clearly on the unit circle. They could be degrees or they could be radians. You can use either one depending on what the problem wants, okay? So this works out really nicely. Let's just jump down here for a second to see how it works, and then we'll talk about it. Okay, so for example, look at this guy. This wants you to find the sine of 75 degrees. All right, well, let's see. I know I left a unit circle around here somewhere. Okay, there is not 75 degrees on the unit circle, but we're on the unit circle. It's just that what we want is somewhere in between here. And we're kind of out of luck because we don't know that value. So if we don't have formulas, we have to put it in the calculator, but it doesn't want calculator because it wants exact. So what these say is that since we're dealing with sine, we would have these choices, one of these. It's telling you to take your 75 and break it into 2 other angles, okay? So if I want to use the plus version, I could take 75 and I could turn it into 45 and 30, right? 45 degrees and 30 degrees. They add together to give me 75. And if I use 45 degrees and 30 degrees, I know the sine and cosine for those. So if I plug those in and use this formula, it's going to give me the answer for 75. Okay? Or if you're just really not an addition kind of person and you want to subtract, you could subtract and do, I don't know, I don't have my calculator out. 2 numbers, like I think 120 minus 45. Does that do it maybe? Let's pretend it does. Okay, so that would be 2 angles that are on the unit circle that you know that you could subtract and get the answer to 75. So the good news is there's a million different ways to do it, right? So you can pick any angles you want as long as they add or subtract to give you the one that's on the paper, okay? Does that make sense? So there's an infinite amount of ways we could all do it. I always tend to just do the easiest and fastest one. I'm not interested in finding 120 minus 45, but you could if you wanted to, okay? So that's kind of the deal. So we have 2 available for cosine, and we have 2 available for sine. All right, you are going to need these for test 2. So that's why, you're not going to need all 4, but I will tell you which one or ones you need so that you can write them on your index card, right? So you don't have to memorize these. Because notice, like for cosine, the sign that's in the middle is opposite of what you get in the beginning. And then cosines stay together and sines stay together. For the sine ones, the sine is exactly what you see here, but then sine and cosine mix. So it gets really confusing if you don't have these written down. That's why to me, it's ridiculous to memorize them because it's so easy to make a mistake, right? Okay, this one is actually my math lab number 1, this addition sine one. They're going to have a drop-down box. They just want you to fill in what the sum formula is for sine. So keep that in mind. All right, let's go down here and start working then. All right, so these 2, I don't know, I think I have written down number 4 and number 7. I don't know which is which, but just write on my math lab 4 and 7. It's the same kind of situation. Okay, here we go. We want the exact value of sine 75 degrees. That means no calculator. Okay, so I'm going to have to choose either this one or this one. I have to decide on two angles that add to give me 75 or two angles that subtract. I was thinking about just doing 45 and 30 and adding them. Is that okay with everybody? That's what I have written down here. Okay, so if I decide I want to do, and you can put them in any order you want. You can do 30 plus 45 if you want to. The order does not matter. So that's completely your decision. Okay, so now it's easiest if you label them. So notice here for the addition one, the first one is alpha. So I'm going to say 45 is alpha. And the second one is beta. So I'm going to say 30 is beta. Does that work for everybody? Okay, now I'm just going to follow the order. Now it wants the sine of alpha. So that's the sine of 45. Then it wants the cosine of beta. So that's the cosine 30. And then it says plus. Then it says cosine alpha. Okay, so that's cosine 45. And then it says sine beta. So that's sine 30. Okay. Everybody see where that came from? We just completely followed the situation. Now, if we had done 120 minus 45, we'd have used this one. If we had done sine of 30 plus 45, we would have had 30s here and 45s here. It doesn't matter. Just pick two numbers that are valid and then label them and follow the pattern. Everybody got it? Okay, now it's just unit circle work. Okay, so I don't have anywhere to put my unit circle. How about there? That's kind of good. Okay, here we go. So what's the sine of 45? Root of 2 over 2. Everybody agree with that? Right off our unit circle. Here's 45 degrees. Sine's root of 2 over 2. All right. Cosine of 30. Here's 30 degrees. Cosine's root of 3 over 2. Okay. Then we have a plus. Then we have cosine of 45. Okay, here's 45. Here's cosine, another root of 2 over 2. All right. And sine of 30. Okay, here's 30. Here's sine, 1, and it's a half. So remember, the beauty of the unit circle is your x values are cosine, your y values are sine, right? So we're just pulling them right off of there. Does that sound okay? Everybody see where these came from? Okay. All right, let's do a little algebra. See if you remember this. Okay, what's the root of 2 times the root of 3? That's root of 6. Yeah, they just multiply. They both stay in their little house, but there they are. I don't know what you just said. Okay,
I was thinking, I was like,
2 times 2. All right, I got a denominator of 4. Can I reduce this, my little eager beaver reducers, this root of 6 over 4? No, why can't I reduce that? Yeah, he's in the radical. You can't go in there and reduce stuff. Okay, plus root of 2 times 1 is root of 2. 2 times 2 is 4. Okay, in trig, they like everything in one nice little chunk. So the answer that they want, I think my math lab will take this, to be honest with you, but the answer you're going to see and the answer everyone wants is root of 6 plus root of 2 over 4. That's the answer that they're looking for, okay? Because you can't combine these, you can't reduce the square root of 6, and it's all over 4. That's it. Sound good? It's not bad.
no, I'm confused.
Okay, no, you're good. Tell me.
So why did we get 4?
Down here?
Yeah.
Oh, because 2 times 2,
Okay.
and then 2 times 2. And then when you add fractions, you keep your denominator.
Oh, so adding, keep multiplying. Okay.
Multiply. Good.
Okay. Thank you.
Yep, little fraction review.
If we did the 120 minus 45,
Uh-huh.
I'm saying to do it, but
Yeah.
would it be longer? Like, the step would it be longer? Or would
No,
it be-
it'd be the same thing. It'd be the same thing. Great question. Okay, so Elizabeth said, what if we had done the other way? What if we had done the 120 minus 45? Well, here we would have had it sine of 120 times cosine of 45 minus cosine of 45 times sine of 120. You could have done that, plugged in your numbers, come out, you would have ended up with this answer. Been the same thing, and it would have been just fine. The only time that it could end up longer and more complicated is when we get to tangent, because the tangent formulas are big giant fractions, and you know that a tangent itself is a fraction. So I would rather deal with root of 3 versus root of 3 over 3. Does that make sense? So then you gotta, I mean, it won't matter. It's just a little more work. Yeah, but sine and cosine, there's really no long or short way. They're both good, easy. Yeah, of course. Okay, so that was pretty good. We dealt with degrees. That was super easy. Let's throw a little wrench in the plan. Okay, look at this beauty. Let's find cosine of 23 pi over 12. What the heck? Okay, so that's obviously not clearly on the unit circle, which means that we are going to need two fractions. Whoops, not even a 4, that's a 12. Hold on. Okay, two fractions that either add together or subtract. I'm an add kind of gal if I can make it work. So I'm going to say we want to add two things together that are going to end up being 23 pi over 12. All right, well, let's baby step it in. What do my denominators have to be? 12. And we know we're going to have pi in the top because that's how radians work. The problem is you go to your unit circle and you're looking for two fractions that have a denominator of 12. You're not going to find one. Look at your radians. They have a denominator of 2. They have a denominator of 3, 4, and 6. And that's it. So where in the world are you going to get two of these? Well, let's remember, if we can break them up, 12 is a great denominator, because if you choose the right numerators, you can reduce these into 2 points you will see on the unit circle. Does everybody see where I'm going with this? So two numbers that will have a factor that will divide into 12. Okay, so they have to add to give me 23. What if I just do, now you can have an infinite amount. I'm just going to choose these two. What if I did 20 pi over 12 and 3 pi over 12? Okay, well, that's great, Ms. Holcomb. They add up to 23 pi over 12, but they're still not on the unit circle. Or are they? Okay, so let's think. All right. I can divide top and bottom of this guy by what? 4. Okay. All right, think bigger. Okay. And if I divide them both by 4, I get 5 pi over 3. Well, look at our unit circle. Look who's sitting down here in quadrant 4, a 5 pi over 3. Okay. All right. What about 3 pi over 12? What can I divide him by, top and bottom? 3, and I get pi over 4. We know he's on the unit circle. So now I have two values that are clearly on the unit circle, and they add together to give me 23 pi over 12. So you can see with degrees, it's super easy because your brain's happy with little whole numbers. But with radians, there's a whole added issue because you have to find two fractions that add or subtract to give you that crazy radian number. And chances are they're not on the unit circle. So when you pick those two, you have to pick two that reduce down. Now, what if I had picked 19 pi over 12 plus 4 pi over 12? Well, 4 pi over 12 is great because that's pi over 3. What am I going to do with 19 pi over 12? Nothing, right? He's not on the unit circle. So that's a bad choice. So you just have to be careful. You have to choose two numbers that add together or subtract, but still reduce down to something on the unit circle. Does that make sense? Something that will, divide into whatever that denominator is. Okay.
Sorry, I was just watching your smiley face.
Oh, I was like, what do you just really love these. Okay. All right. Does that make sense how we got those there? It took us a minute, but we came up with some. So there are other options. That's just what I came up with. But there's a lot of options that don't work too, right? They'll add together to give me this, but they don't reduce to unit circle stuff. Okay, is that all right? No. Okay, here we go. So here's your alpha Here's your beta. Okay. All right. Well, and this, be careful here. This said cosine. So now we want to do cosine. We found our alpha. We found our beta. Okay. There we go. So you can look back up at the top of your paper here and follow along with the cosine sum. So here we go. We're going to have cosine of alpha times the cosine of beta minus, even though it's a sum, sine alpha times sine beta. There we go. Okay. Oh, good. And there's unit circles back there. If you guys have lost yours or gotten rid of them, there's a whole stack. All right, now we're ready for our unit circle. So 5 pi over 3, he's way down here, okay, in quadrant 4. My cosine is 1/2. All right, what's the cosine of pi over 4? He's root of 2 over 2. Remember, that's 45 degrees. That's the one where they're both the same. They're both 45 or root of 2 over 2. Okay, then we're going to have a minus. Then we want 5 pi over 3. We want the sine now. Now watch your sign on your sign. It's negative root of 3 over 2. Thank you, Elizabeth. Okay. Negative root of 3 over 2. Okay, be careful with him. You're going to be adding this second part, it turns out. And then sine of pi over 4 is root of 2 over 2. Okay. All right. Now we're going to combine them. 1 times the square root of 2 is root of 2. 2 times 2 is 4. All right, remember, this is minus a negative, so now we are plus root of 3 times root of 2, root of 6. 2 times 2 is 4. Clean that up a little bit, put it all over 4, and there's our answer. It's pretty much, it's exactly the same answer as A. They end up with a lot of the answers being the same, to be honest. So, okay, sound good? Not too bad? All righty. Let's do a subtraction one, and then we're going to go the other way. Everybody okay on that? Got it? Okay. All right. Okay, so now we want the exact value of sine pi over 12. Okay, how do I know this is a subtraction one? Well, if you have a really giant big chunk of something, it's easier to add two things together to make the chunk, right? If you have a little bitty thing, look, his numerator's 1, then it's going to be easier to subtract two things to get the smaller number. That's just kind of, you know, how it works. So, okay, sine of pi over 12. He's not on the unit circle explicitly. We're going to have to come up with two numbers that either add to give you that, that's not going to work, or subtract to give you that. Okay, so here we go. Let's think. If we have pi over 12, what are two numbers that we could subtract? Remember, these have to be over 12 with pi's in the top. That would give me a 1 in the numerator. 4 and 3. You could do 4 and 3. You could do 3 and 2. You could, you know, there's a lot of different options there that you could make work for you. These are going to reduce down to pi over 3 and pi over 4. Okay. If you had done 3 and 2, this would have reduced down to pi over 4, and 2 pi over 12 would have reduced down to pi over 6. We have that too. So you have a lot of options. Okay, awesome. So this is alpha. This is beta. Everybody okay with how we got that? Okay. All right, we have a sine. And we're going to subtract. Make sure you put these in the right order. It's hard to see what order they go in once they've been reduced. But remember, this was the first one. Subtracting this was the second one. So this is your alpha, pi over 3. Pi over 4 is your beta. Okay. All right, so if you need to flip back to the first page, it's been a long time since I've done these. I got to flip back for mine. Okay, so for the minus sign, we have sine alpha, so sine pi over 3, times cosine beta, that's cosine pi over 4, minus sine, oh, they put cosine first, my bad. Doesn't matter when you multiply them, but cosine of alpha, sine of beta. Sorry, I ran right smack into my other thing. Okay. Everybody okay with that? Okay. All right, now we go to our unit circle. Here we go. Okay, so sine of pi over 3, here's pi over 3. Sine is root of 3 over 2. Okay. Cosine of pi over 4, that's our root of 2 over 2. We have a minus. Okay. Then we've got cosine of pi over 3, that would be 1/2. And sine of pi over 4, that's root of 2 over 2. Okay. Everybody okay with that? All right, we're going to clean it up. We get a square root of 6 over 4 minus a root of 2 over 4. And we end up with root of 6 minus root of 2 over 4. You can see it's really just kind of the same. Sometimes they're subtracted, sometimes one's in front, sometimes another one's negative. It's like the same combination always for these. Okay, sound good? All right, well, you did great because you did, all right, this side on the left and you turned it into the side on the right and gave us the answer we needed. I don't know why they do this, but it's super easy, so I'm okay with it. What if they give you the right side and they want you to go back the other direction? Okay, well, we can do that. That's not bad. Let's look at that. So this one says, find the expression equivalent to sine 80 cosine 40 plus cosine 80 sine 40. Then find the exact value. All right. Oh, by the way, I'm sorry. C was my Math Lab 6. This is my Math Lab 8. Let me go ahead and tell you E before I forget. My Math Lab 9. Okay. All right. So one thing we could do, just because we're starting out, let's write this, right? Just so that we can see what they're giving us. That's what they gave us. That's what they want us to find. Okay, well, none of those are on the unit circle, but they do equal exactly one of these guys down here. So let's see. I have sine, cosine, plus cosine, sine. Okay, well, here's sine, cosine, plus cosine, sine. Does everybody see that? This is this. Bless you. Does that make sense? Do you see how I matched it up? Sine, cosine, plus cosine, sine. Sine, cosine, plus cosine, sine. So this is alpha. This is beta. Again, this is alpha. This is beta. So this is the identity or the formula, this sum of sines that we're looking for. Okay, so here we go. We're looking for sine alpha plus beta. That ends up being the one that we found. Does that make sense? We just matched it up. There were 4 choices. 1, 2, 3, 4. We matched up the pattern with the sum of sine. There's only one of them it could have been. Okay, that meant alpha's 80, beta's 40. Okay, add them together. This meant this is the equivalent expression, the sine of 120. That's what they wanted, the equivalent expression. Now, they also want us to go on to find the exact value. That means we're going to go to our unit circle and find the sine of 120. Here's 120. Our sine is root of 3 over 2. There we go. We did it. We just went the other way. Easy enough? Okay, let's see if we can pick out which of the 4 this guy is. Okay, all right. Now I'm looking for cosine, cosine minus sine, sine. All right, well, here's cosine, cosine minus sine, sine. So to me, I think it's the sum of cosines. What do you think? Everybody agree with that? Okay, so that means 25 is alpha, 20 is beta. Okay, and this is going to be cosine of alpha plus beta. That's the one we're looking for. So if I write that over, it's going to be cosine of 25 plus 20. Okay, that's going to be cosine of 45 degrees. Okay, everybody okay with that? Now, this one for E did not want the equivalent expression. This one just wants the exact value. So that's when I have to go to the unit circle and find the exact value of cosine of 45 degrees, which is going to be root of 2 over 2. And that's my answer. So this is exact value. This is equivalent expression. So depending on what they ask, so you don't get them confused. Exact value is this is equivalent expression. Okay, so you just pick it out from the 4 options. All right, let's try another one of these with radians. Okay, where's Summer? You were doing just fine. You're fine, you're fine. You're not bothering me. I just feel bad for you. Okay, don't run over there and give her the Heimlich. She's just coughing.
Oh, I'm not certified.
Okay, all right, here we go. So again, wants the exact value. That means we're going to have to go to the unit circle. Okay, all right, this is going to be a little tougher. All right, but let's first pick out our formula. We have 4 choices. So I see sine cosine minus cosine sine. Okay, sine cosine minus cosine sine. Everybody okay with the difference of sine down here? Okay, so this is my alpha, this is my beta. And it's going to be sine alpha minus beta. That's what we're looking for. Okay, here we go. We're going to put sine of pi over 2 minus 3 pi over 4. Okay, so already we have a little algebra issue. Why can't I immediately subtract these guys? I need a common denominator. Okay, so my common denominator is going to be 4. Everybody see that? That would be the lowest common denominator. Oh, it's like, oh, Elizabeth, okay. All right, so 3 pi over 4 is fine. Let's change pi over 2. So if we take pi over 2 over here, we want to turn him into something over 4, right? We could multiply top and bottom by 2 and get 2 pi over 4. Okay, easy enough. That becomes 2 pi over 4 minus 3 pi over 4. All right. I know you guys don't like anything weird, but it's good for you to have a little weird sometimes. So here we go. What's 2 pi over 4 minus 3 pi over 4? That's negative pi over 4. That's okay. You're allowed to have something weird every once in a while. We can do negative pi over 4. All right, so let's think about this. If this is my unit circle, this is positive pi over 4 up here. Where's negative pi over 4? Right here, right? It's the pi over 4 situation in the 4th quadrant, right? Negative pi over 4. So I want sine negative root of 2 over 2. There we go. Okay, there's my answer. Sound good? Not terrible. Okay, let's use these formulas to establish some identities then. We need to be careful here. I want to really show you the difference in something. Let me go back. Let me see, where's my page? Okay, you have been trained your whole life, your little parenthesis assassins, right? You have been trained your whole life that when you see something outside parentheses, you distribute. You're getting rid of them. That's what you've been trained to do, which is true, except you have to be really careful in trig. This, you cannot distribute. You can't distribute this. Why can't I distribute cosine through there? Because cosine's not a thing. Cosine theta is a thing that could be distributed. Cosine pi over 2 is a thing that could be distributed, but the word cosine can't be distributed. He has to have something after him. So for example, okay, if we go back to what we were doing in the last section, I can distribute this. Everybody see that? Because he's cosine theta. So I distributed him through there, the theta with him. He's all one thing. When you see this or this, that is not a distributed situation because there's nothing after the word. These mean that you have, I got stuff everywhere. And I have completely, these mean you have these situations. See how it's the word in front of two things being added or the word in front of two things being subtracted? See the difference? This is not a distribution situation. It's a formula that you follow. So when you see this, you haven't had to deal with that before. You cannot distribute. I get a lot of students on tests that want to say, oh, that's cosine pi over 2 minus cosine theta. You can't do that. You can't just distribute words through things, okay? This means the difference formula for cosine. This is what you should be writing. Is that clear? You got to be really careful. It's a tiny little distinction. If this said cosine theta, then you could distribute it, but it doesn't. It's just the word. So it's no distribution, okay? This means I have to use this formula, okay? So this means this is alpha and this is beta. And I'm going to need to do this with this. That's what that means, okay? All right, so we haven't had a situation like A yet, where A isn't telling you to turn it into the right side. A is telling you, give it a whirl. It might work, it might not, okay? So if it works, you'll put true. If it doesn't, you come up with something else, you put false, okay? It's kind of strange, but that's math stuff for you, right? So here we go. Let's see what this gives us. So this is going to be a cosine of alpha. So cosine pi over 2, cosine beta, which is just cosine theta in this case. This is kind of strange, but we're just going to plug it right in, plus sine of alpha, which is pi over 2, times sine beta, which is sine theta. Okay. Everybody see that? We just followed the pattern. Our alpha and beta were weird, but we did it. We're going to see what shakes out. Okay. All right. Now there's nothing I can do with cosine theta and sine theta. I mean, they're just kind of like placeholders. It's like an X would be in algebra. But I can look on the unit circle for these guys, right? So let's look on the unit circle for cosine pi over 2. All right, here's pi over 2. Cosine is 0. Okay, so we'll just stick him in front. All right, then it wants the sine of pi over 2. Okay, that's going to be 1. Okay, 0 times anything is 0. And all I'm left with on the left now is sine theta. There's nothing else I can do with sine theta. It's like having an X. There's nothing else to do. So does this left side equal cosine? No, it equals sine. So it's false, okay? Oh, I'm sorry. F, I'm really bad at this, huh? Okay, F is my math lab number 10. This A is my math lab number 2, believe it or not. And then B, which we're going to squeeze in, is my math lab 13. They're all over the place. Okay. All right, so A was kind of true, false. Let's see. B, we're back to, yes, this is real, make it work, establish the identity. We're going to turn this into this, okay? So we're going to do the same situation. Do you see here? You cannot distribute the word sine. This means you have to go to your sum formula for sine. So if I do that, you can barely see it, but there it is. My alpha is pi over 2 and my beta is theta. Okay, it's like a bad nursery rhyme. All right, here we go. We're going to do sine of pi over 2 times the cosine of theta plus the cosine of pi over 2 times the sine of theta. Everybody okay with that? We just copied it right out of there. All right. Okay, so again, I can't do anything with the thetas, but I still have the pi over 2 situation. So I'm going to go to my unit circle. Here's my pi over 2. My cosine 0. My sine is 1. So I'm going to have 1 times cosine theta plus 0 times sine theta. My 0 cancels. And sure enough, there we go. Now let me just talk to you about the next page. We're not going to do any examples, but hold on before you start wrinkling papers from here to high heaven. So hold on. Okay, so everybody okay with B on here? You used them now to establish an identity. Okay, so we talked about sum and difference formulas for cosine and sine. Here comes tangent. So tangent is always more complicated, right? Because by his nature, his definition, he's a fraction. He's sine over cosine. So he's always a little harder. He's not explicitly on the unit circle. You always have to make it happen. He has to be rationalized a lot of times. If he has that root of 3 or root of 2 in the bottom, that becomes an issue. So we're going to get into some algebra, some pretty high level algebra, higher than college algebra, actually, when we start doing some of these tangent problems. But it's fine. It's the same thing. You're just going to take it one step at a time. But Elizabeth brought up a good point at the beginning where she said, would picking some numbers to add or subtract make things easier than picking other numbers? Well, for cosine and sine, no. But for tangent, yeah. So we're just going to kind of look at that and go through there. We just have 3 pages, I think, left on this. 3 examples, yeah, and we're done. So you're not going to be able to do all of 7.5 unless you go online and look at my notes and take off, which I encourage you to do. But we will finish this Friday, and then we'll look into 7.6, okay? So I will